Hi, sixth graders, this is Mrs. Gall. Today we're going to talk about quadrilaterals and polygons. Get your notebook open to a fresh page and press play when you're ready to continue. What do you already know about quadrilaterals? Maybe you know that they have four sides, which also indicates they have four angles, four vertices. A vertex is when two lines come together to create a point. We have different types of quadrilaterals that can be classified by sides and angles, and the sum of the interior angles must always be 360 degrees. Since we know that all the angles add up to equal 360, we can find missing angle measurements by using that knowledge. So let's take a look at this quadrilateral. We see that we have one angle measurement that's 75 degrees, one marked as x degrees, so that's an unknown, one marked as x plus 7, and then a box here which indicates 90 degrees. So what we can do is we can actually add all of these up and set them equal to 360. From there we can combine like terms. So I have an x and an x, those can be added together to get 2x, and then 7, 75, and 90 can be added together to get 172. From here, I just have a two-step equation. So I subtract 172 from both sides. I get 2x equals 188. And now I can divide both sides by 2 to figure out what just x is. So x is 94. So that tells me this angle's measurement. Now let's figure out the other missing angle, which was x plus 7. So we can plug in our x. If we add 7 to 94, we should get 101 degrees. So we have 101 degrees for this missing angle measurement and 94 degrees for this missing angle measurement. You try one of those on your own. Can you figure out the two angle measurements that involve x by adding these together and setting them equal to 360? Hopefully when you add them together, you see that you have 3x, and 124 plus 65 would give us 189 for the constants. And remember, we want to set that equal to 360. Subtract both sides by 189, divide by 3. You should end up with 57 degrees for x, and then 57 times 2 gives us 114 degrees for our other side. Let's move on to classifying our quadrilaterals. So we kind of have a family tree that we're going to go through here. At the top of our family tree is a quadrilateral, meaning we have a figure with four sides and four angles. That's kind of those main things that a figure needs to be considered a quadrilateral. Off to the left of our family tree is a trapezoid. A trapezoid has one pair of parallel sides. These two sides marked with the triangles will move on and on forever and will not touch because they are going parallel to one another. On the other side of my family tree, I see a parallelogram. Parallelograms are unique because they have two pairs of parallel sides. So the trapezoid only had one pair, but the parallelogram has two pairs. And then you see these little tick marks. Those are telling us that we have two sets of sides that are congruent, meaning they're equal in length. So the top and bottom are equal in length, and then the pair of the sides are also equal in length. From our parallelogram, we have more specific types of parallelograms. So you'll see down to the left here, we have a rectangle. What's special about a rectangle, it has all of the things a parallelogram has, but it also has four right angles. On the other side to the right, we have a rhombus. A rhombus has all the things a parallelogram has, but it has something a little bit more specific, four sides that are identical in length instead of two pairs. So all four sides are identical in length. A rhombus a lot of times will remind us of a diamond shape or maybe kind of that square that shifted a little bit, so we won't see those perfect 90-degree angles with the rhombus. Below at the very bottom, we see our most specific type of parallelogram here, which is our square. We have all four sides are equal. All four corners are 90 degrees. Okay, so you may have heard people say before, oh, a square is a type of rectangle. It is, but it's more specific because we have all four sides being equal, so we would call it a square. Let's practice classifying some of these quadrilaterals. I apologize, it's a little blurry. We have two sets of congruent sides and four 90-degree angles. That would be a rectangle. Ooh, what about this one? We have one pair of parallel sides. Although we have two 90-degree angles, the 90-degree angles aren't really going to do very much for us unless all four of them are 90 degrees. So since we only have one pair of parallel sides, if we go back to our figure, that was a trapezoid's definition, was one pair of parallel sides. So that would be a trapezoid. Four sides that are equal, four 90-degree angles, that would be a square. And our last one, we have these two are congruent, and then this set is congruent, but not all four are the same. So it's not a rhombus. It actually isn't even a parallelogram because we would need parallel sides, and those are not parallel. So this would just be a quadrilateral. We're going to move on to polygons, the second half of this lesson. So a polygon is a simple closed figure with three or more sides. Please pause to write that down. A regular polygon is a polygon with all equal sides and all equal angles. Please pause if you need more time to write that down. How many polygons do you know? Some of our most common polygons are 3 sides would be a triangle. What about 4 sides? Quadrilateral. 5 sides? Pentagon. 6 sides? Hexagon. 7 sides? Hepta or septagon. 8 sides? An octagon. 9 sides? Nonagon. 10 sides? Decagon. 12 sides, dodecagon. 20 sides, I'm going to say this wrong, icosagon. I might have said that wrong. And 100 sides, hectagon. N-sided polygon would be called an n-gon. So we could put any number there and just call it 77-sided polygon, 77-gon. A diagonal is a line connecting two non-consecutive vertices. Remember, vertices are kind of our corners. So if we're looking for a diagonal, it would have to be a corner that's not right next to the corner that we're looking at. So here's a vertice, not this corner because that's right next to it, not this corner, but this corner over here is a non-consecutive vertice. And an interior angle is an angle on the inside of a polygon. So I could kind of draw that little arc there to show that is an angle. Let's kind of look for a pattern here. So if we were to add up interior angles of a triangle, there's actually no diagonals on a triangle because there's only 3 sides. So there's no vertice that's not right next to the current vertice that you're at. So 0 diagonals, 180 degrees for our interior angles. Quadrilaterals, we just talked about those. 4 sides. There's 1 diagonal, and that's 360 degrees. Pentagon has 5 sides. That gives us 2 diagonals and a sum of 540 degrees. Hexagon has 6 sides, 3 diagonals, and 720 degrees for the sum of interior angles. Octagon has 8 sides, 5 diagonals, 1080 degrees for the sum of interior angles. Have you picked up a pattern? Could you make a rule to find the sum of the interior angles of any polygon? What do you notice the connections between some of these numbers that we've placed? Here's our rule. Take the number of sides in your polygon, subtract it by 2, and then take that number and times it by 180. You will get the sum of your interior angles. So let's look. For example, a heptagon is 7 sides. So let's plug in a 7 here. 180. I think that might be up here. No. Okay, 180 times 7 minus 2. Notice 7 minus 2 is in parentheses, so I want to take care of that part first. 7 minus 2 is 5. Grab my calculator to take 5 times 180, and I will get the sum of my interior angles, which is 900. Ooh, a decagon. How many sides does a decagon have? 10. Will you go ahead and find that? If I take 180 times 10 minus 2, I get 8 times 180, 1,440 degrees for the sum of the interior angles of a decagon. So that is a formula that we can use for any number of sides. So here's an example where you might just see that number plugged in as a 15gon. If I plug in a 15, try that, 15 minus 2, 13 times 180, I got 2,340 degrees. All right, you guys, that's all I have for you today. Check in with your teacher if you have any questions.